1 gigahertz in this range, right? Coaxial cables. Next, it is waveguide or can be space channel. So here also atmospheric channel is used for shortwave radio and long wave radio. You see the different models and schemes are there. AM, FMs. You see here the applications are there. AM broadcastings, aeronauticals, submarine cables, navigations, transoceanic radio, right? This the frequency range is used in these applications. Next, you see mobile radio, VHF, TV, FMs, mobile aeronauticals, around 900 megahertz, mobile system it is used. UHF TV. Next, they are the frequency ranges for different satellite and microwave applications. So you see, this is a frequency range used for the communication systems from 300 hertz to up to 90 to 100 gigahertz, right? Of electromagnetic wave spectrum, electromagnetic spectrums. These frequencies are used for different communication systems with different models and schemes, right? That is another region is also there that is used for these optical optical. Another region is here which is called the optical regions. Here you can see frequency, it is around 10 to the 14 to 15 hertz, right? In fact, you see first is infrared, next it is visibles, and next is ultraviolet. So the whole spectrum, you see it, audio, VLF, low frequency, medium frequency, high frequency, very high frequency, ultra high frequency, super high frequency, millimeter waves, right? Millimeter waves. And next it is the apart from these things, there is also another region is here, another region that is used for communications. That is the infrared regions. Visible, of course, it is not used for communications. Anyway, here it is shown it here, but in some cases also this range is used. So you see it here. You see the optical fiber is used in these regions. It is far infrared to infrared, or not the visible spectrums. Visible, it is it is 400 to 700 nanometers. Ultraviolet, it is around 400 nanometers, and red, it is around 700 nanometers. So below 700 nanometers means around 1.6 microns, right? That is used. 1.6 micron. Here it is 2.55. It is shown here. Of course, this is far infrared, but actually it is nowadays it is up to, it extends up to 1.6 micron regions. So 0.8 micron to 1.6 micron regions. This region is used actually for optical fiber communications, right? Initially it is for for voice signal it is used. Nowadays it is for every communications. I mean multimedia, voice, data, video, teleconferencing, video conferencing, etc. For all cases now it is used, right? And the frequency range is most interesting. Here you can see it is 10 to the power 14 to 10 to the power 15 hertz in these regions. That's why huge bandwidth they can have it. It can beat any other communication systems because of its extremely high carrier frequency, 10 to the power 14 to 15 hertz. Some numerical examples also you, even in terms of bits also, number of say 1 voice signals, it is 10 to say 64 kbps is required, right? So you can calculate if you use in this frequency range, millions of voice signals or speech signals can be transmitted in this range. Of course, that depends upon the other facilities, means sources, detectors, those things are also involved. But theoretically, millions channels can be transmitted through optical fiber because of its extremely high frequency regions, 10 to the power 14 to 10 to the power 15 hertz, right, in these regions. right? So this is the whole arithmetic wave spectrums, right? And here you can see earlier communications, before fiber communications, it is extends up to millimeter waves, but you see another region is here, which is infrared regions, which is used for optical fiber communications. Next, you see the different transitions of the multiplexing schemes that we have seen it. This is the hierarchy used in US telephone network. We have seen it. This T1 rate. It is it's a time division multiplexing when we have discussed in last semester. We have seen this 1.544 Mbps. That is for 24 voice signals, right? So 64 kbps per signal. So 24 plus from extra bits are there that constitutes the 1.544 Mbps. That is a T1 rate. Next, it is T2 rate. It is 6.312 Mbps. Next, T3, T4, like these things. There are different hierarchies used in US, right? And if you compare, just I mentioned, compare their voice signals, you see rate and the number of voice channels. You see it is proper T1 it is 24, next T2 96, next it is 672, 4032, like 6. And this is in US, and there are the different hierarchies in other countries other than US. Right. And another version is used in optical fiber system hierarchy. That is actually, we have seen this SONET, synchronous optical network, that is in US, and in India, like it is used, the term is SDH, synchronous digital hierarchy, and SDH. So in that case, there are also termination multiplexing is used. In this case, it is called STS. STS, synchronous transport signals, right? STS, that is when it is converted to optical domains, that is called optical carrier ones, OC ones. That is the rate. It is Mbps, 51.84 Mbps. Similarly, for OC3, like OC9, etc., they are the different SONET levels in US, and in India, like countries, it is used STM. These are the STS, different STS rates in terms of OC. And in India, it is called STMs. In any BSNL cables or Reliance cables, see there that STM is written, synchronous transfer modules, right? That corresponds, that starts with 155.52 Mbps. That is STM1. So around these ones, see, for different STM ranges, you can have different STMs. You can have different data rates. These are the different SONET levels. Right? We'll see it, SONET frame structure. To some extent, we have seen it. Also, when we discuss the SONET ring network, that times these things will be discussed to some details. What are the different sections, and what are the different aspects when you consider the fiber ring networks, LAN, and fiber LAN, where ring, mesh, bus, those things are used, right? So this is the SONET, different SONET levels used in fiber communication systems, right? And if you see the different generations of optical fiber systems, you see initially it started with this 800 nanometers with the multimode fibers. Right, multimode fibers, and that times it is data rate. It was around 90 Mbps. Maximum you can have it at 100 Mbps in this range, right? Initially, it started with these 800 nanometers, right? In fact, fiber optic communications, optical fiber was developed, but the low loss fiber was developed in 1970. So after that, actually, the fiber optic communications were implemented, right? When the low loss fibers were available, right? AT&T, Corning Glass Works, etc. They are the reputed constants. They started the optical fiber communications. Right. And these are first generations of optical fiber systems using 800 nanometers with multimode fiber. Next, it is 1300 nanometers. It started 1300 nanometers single mode fibers. Here, of course, single mode fiber is used here. Uh, in this particular wavelength, you see the a particular dispersion effect was minimum, and bit rate, data rate or data rate was increased up to 4 Gbps. Earlier it was 100 Mbps. Now in this case it increased to up to 4 Gbps, and also repeater spacings also has been increased to 40 kilometers, right? And simultaneously, undersea fiber cable systems are started. That is around 300 Mbps, right? With single mode fibers, 1300 nanometer of fibers, right? Single mode 1300 nanometer fibers, right? So this is the second generations. Third generations actually started in 1550 wavelengths. 1550 wavelengths, you see, after 1980, you see 1550 nanometers. At this typical wavelength, attenuation is minimum. Of course, attenuation is less, but overall attenuation will be is minimum at 1550 nanometers. But some dispersion effect will be there. But at this particular wavelength, we'll see a particular dispersion can be compensated by another dispersions. In fact, dispersion limits the data rate, or attenuation limits the repeater spacing. I mean, if the attenuation is more, that means a number of repeaters will be less. And if the dispersion is less, then you can have high bit rate, high data rate. Right. We'll discuss in details these dispersions and attenuations. But at this particular wavelength, both attenuation and dispersion were less, and in fact, at this particular wavelength, we can have very high data rate systems and very longer repeater spacings were obtained in this between 50 nanometers, and where both attenuation and dispersion were minimums. And at this point, in LANs, 5G LANs, etc., TV distribution, those have been started with 5G systems. And the next third generation, the fourth generation actually started with this, with coherent detection scheme. There are different detection schemes are there, coherent detection schemes, and with optical amplifiers. In fact, here we'll see it. Different optical amplifiers are used, and with these amplifiers, here the bit rate greater than this 5 Gbps, we can have it over a longer repeater spacings. Right. In fact, if you use the optical amplifiers, the several 100 kilometers, there will be no need of repeaters. Right. In fact, repeaters can be replaced by optical amplifiers. Repeater means, you see, you have detectors, electronics, and sources. A whole system would be there in a concise forms. But in amplifiers, simply just like amplifier, there is no, of course, here optical amplifier is there, there is no need of conversions. For repeaters, you need conversions, optical to electrical, next electrical to optical. When you do the conversions, then many things are added, many noises are added, many other limitations are there, will be included if you do the conversions. But if you instead, if you use the optical amplifiers, there will be no need of such conversions, and simultaneously you can increase the distance as well as you can have high bit rate systems. So these are the different generation schemes. I'll just show you what are the technology involved in those different generation systems. One slide is here. Before that, you'll see what are the attractive features of fiber optic systems. You see, First is just first is you see it the low loss and wide bandwidth is a one of the most important advantage of hybrid systems. Low loss and wide bandwidth. Low loss, you see, it is less than you can have it 0.2 dB per kilometers, even 0.16, 0.15 dB per kilometer can be achieved with this nowadays available, right? And if it is very, very low loss systems, then you see, obviously, the repeaters spacing will be quite large. For microwave or any other things, you can just only after 10 kilometers, you need repeaters. But in optical fibers, up to 200 kilometers, 250 kilometers, there will be no need of repeaters. And a number of repeaters less means your cost will be drastically reduced. Right. So it has a very, very low loss systems. In turns, you can have very high data rate, very high repeater spacing systems you can have it. And second is this, you see, wide bandwidth. Why it is wide bandwidth? Because you see, it is carrier frequency, or I just mentioned 10 to the 14 to 10 to the 15 hertz, right? So very wide the bandwidth is here of the terahertz. So if the bandwidth is large, means we have seen this in data communication systems bandwidth related to data rate. So data rate will be enormously increased in this case. The data rate or bit rate will be very, very high because of this wide bandwidth. In fact, you see the basic backbone is optical fiber. If you all other communication systems are there, mobile you are using, but that is for wireless system. But tower to tower or different, I'll show you in India how the connections are there, how we are having these connections, internet, etc., internet networks. It will be clear. Most of the connections are through backbones are through optical fibers. Only tower to your mobile or users, this is wireless. But other than it is through optical fibers. Right. So that is the first ones. Very, very low loss systems and very high bandwidth systems. Next, it has very, very small size and lightweight. Small size. I'll just show you the different dimensions of optical fibers. That is, I'll say if it is a single mode fibers, then you see it will be 2 to 10 microns. Small size, it is if it's SM fibers, it is 2 to 10 microns. See, it is thinner than hair in diameters, right? Whereas if you see conventional cables, it's quite large compared to these things, right? SM fibers. Of course, total dimensions, it is 2 to 10 microns. It is the core diameters, and the cladding will be of 120 microns. And surround this, there will be another jacket. So overall dimension is very less, and that will be very, very useful for replacement of these heavy bulky wire cables in crowded underground city ducts or the trays, etc. Right, and it is of great importance in aircraft, satellites, ships, where lightweight cables are highly desirables, right, in military applications also. So it has very, very small size and lightweight, extremely lightweight, and that's why it is very, very useful in aircrafts, ships, submarines, etc. Those things are there. Typical dimensions, I'll just show you SM fibers. Different types of fibers are there. To some extent, we have learned SM fiber, fibers, SI fibers, GI fibers, etc. Though different types of fibers are there, right? That will see it. Next, you see your immunity to interference, right? Here, fibers are purely dielectric in nature. In fact, fiber, I just mentioned the dimensions. Actually, there are 3 layers are there: core, clad, and next jacket, right? If you see these ones, actually, I'll just show you the fiber structures. So there are 3 layers are there, right? This is core, clad, and jacket. Right. and these covalent clad generally they are made of glass or can be glass and plastic like these things. Hello, একটু ক্লাস আছে এখন, ওই একটা সময় ক্লাস শেষ হবে তারপর। So there'll be so here you see energy is well tracked within this core, and here we'll see that production of energy, that is energy is well trapped within the core, and that is it is not, since it is dielectric in nature, made of glass or plastic, so there'll be no it is non-conducting, non-inductive, non-relatives, right? Non-relative, non-inductive, non-conductive, non-relatives, right? Non-inductive, non-relative, right? Non-relatives, non-conductives. And so these things are there because of its dielectric natures. So there'll be no electromagnetic interference. It is safe for it is immune to electromagnetic interference. So inductive pickup for signal carrying wires or interference due to lightning. These are what the problems will be absent in this case, right? That's why it is very, very useful for military applications also. And also this, because of the similar natures, dielectric fibers are dielectric, and it is electrically insulated. There is no electrical signal here, so there'll be no electrical crosstalk. No crosstalk will be there. So high electrical isolations are there. I mean, one fiber to another fiber, there'll be no such signal will be there. Crosstalk will be almost absent in this case because of its high electrical isolations. That is because of dielectric nature of optical fibers. Next, you see the signal security. A high degree of security is there in optical fibers because just I mentioned the energy is well trapped within this fiber. So there'll be no inactive pickups or right. There'll be no tapping is possible because it's the well trapped the energy propagations within the fiber. So high degree of security is there, and that's why it is very useful for banking, computer networks, or military systems because of its high degree of security, right? Another distinct advantage is there. You see abundant raw materials. Fiber is made of glass, generally made of glass for low loss fibers. Both core and clad are glass. So glass means it is silicon or silicon oxide. We'll see the fabrications materials. Silica and the principal source of silica is sand, which is plenty in nature. So it is which is abundant in nature. Because sand is the principal source of silica is sand. So once the technology is developed, it will replace all other. It can replace or any other cables because of its abundant raw materials. So expense will be drastically reduced in this case. Right, it's a source of the silica. It is sand. Next is flexibility and reliability. You see here, great deal of flexibility is there in 5P systems because suppose you have implemented 5P systems initially for certain Gbps systems. Suppose it is a 10 Gbps systems. Next, you see because of this the requirement, you see it needs to change it for say 50 Gbps systems. For other systems, you have to change everything. You have to change the cables, you have to change the sources, detectors, etc. Everything's here. But here, there is no need of changing the optical fibers here in this case. The same fiber can support 10 Gbps, 2 terabit per second. Even it is possible several tbit per second, tbps, terabit per second, right? So Gbps means 10 to the power 9. Right? Mbps means 10 to the power 6, and terabits means 10 to the power 12 bits per second, terabit per second. And so, so extremely high bit rate systems is possible without changing the cable. Simply, you have to change the terminal electronics. That's all, right? So, great deal of flexibility is here. And also, it is highly so it is that's why it is in here. You can see can be changed from low data rate to high data rate systems. Also, it is highly reliable because you see optical fiber is made of glass. There is no need. There is no electronics within this optical fiber, and signal is optical signals. So for any optical systems, once it is established, it doesn't need any servicing. If you can see it in microscope, telescope, etc. In optical systems, very less servicing is required. Whereas for any electronics, pure electronics component, you see, it needs servicing every 6 months. You have to change the chip or any other things are there. So high reliability is here, and great deal of flexibility and reliability is here. And present global scenario, you can see it here how the optical fiber is implemented in different continents undersea through undersea cable systems. You can see it here. Almost 99% of the bandwidth is through undersea cable systems, where different continents are connected optical fiber cable system. That is single mode fiber through single mode fibers, right? That is the scenario for the entire world, right? All the continents are connected to other one continent connected through undersea cable systems. In India, I told you how you see though are using the mobile, but actual backbone is optical fiber. You see how the backbone links are through optical fibers. You see there the different links are there. The circles are the point of presence. POP, these are called POP, right? Through POPs, getting in the different internet connections, etc. Those things are there. This is the National Knowledge Network, right? The different things are there. So they are the Indian scenario optical fiber systems. Now, if you see a little bit about these optical communications, in fact, other than optical fiber communications, also optical communication exists. That is actually optical wireless communications. Nowadays, it is also focused on visible light communications. LEDs are, room light is used. Generally, room light is based on LEDs, light emitting diodes. That light also can be used for communications. So, and that is called visible light communications. That is a part of optical wireless communications. And also people are trying with the establishment Li-Fi, just like Wi-Fi. Li-Fi is here. If it is based on light, then you see for downloading one movie, it will take a fraction of a second. Within 1 second, where nowadays, at present, it requires several minutes. But here you see, if it is based on Li-Fi, within fraction of second, or not even 1 second, less than 1 second, you can download a movie, right? So different communication systems are there on optical wireless communications, and also you see there is guided communication, there is fiber optic communication. So optical communication based on the either guided, it can be unguided. We will focus at this moment on the guided optical communication, that is through optical fibers. Right. Optical wireless communication, of course, it is not for very long distance systems. It is maybe for building to building, right? Within a buildings, right? Within malls. Suppose in a mall, several computers, 100 computers are connected. Then they can be they can exchange the information very high speed through optical wireless, right? But in optical fiber communications, a very long distance, it can beat in others. Communication systems over distances, very low loss systems, right? And also repeater spacing is quite large, and also it has very high bandwidth. It supports till terabit per second, right? So this is the optical communication systems, and I told you different generations are there. So if you see the generations, you see it here. The first generations I told you it is at 800 nanometers. So actually it is 850 nanometers, right? it is 850 nanometer. It was based on semiconductor lasers initially, right? And repeaters spacings around 10 kilometers, right? In this case, right? And that times multimode fiber is used. That is the 5 dB per kilometers, right? In the first generation. So the first generations, these things are there. That is around 800 nanometers, and repeater spacings around 10 kilometers, and the bit rate it is around 50 to 100 Mbps, and then based on fibers. So mainly here the problem was the distance is limited because of the attenuations. That times you see it is of attenuation is of the 5 dB per kilometers, right? Next generations, I told you it is at 1300 nanometers. You see here, of course, the same semiconductor layers are there. Repeater spacing has been increased to 50 kilometers, and bit rates around 2 Gbps, Gbps. And in this case, single mode fiber was used, but of course, attenuation is less. It is 0.2, 0.5 dB per kilometers in the second generations. Because of this low loss, it is repeater spacing has been increased, but still it is limited by the attenuations of the fibers. This is second generations. Third generations, you see, in the earlier simple lasers are there, but in the third generations, semiconductor lasers, DAB lasers are there. DAB lasers, distributed cable. We'll see what is this distributed pair. We'll see this also why it is 3-pipe compound semiconductor lasers. In fact, LEDs or lasers that are used for fabric systems, it is based on 3-pipe compound semiconductors. That is not based on silicon or germaniums. They are actually indirect bandgap types. So their efficiency is less compared to these direct bandgap types. So that's why these compound semiconductors are there. And that too, all DAB laser, distributed feedback lasers, we'll see it is highly coherent. Once it is talk about the lasers, that means coherent beam will be obtained both in temporal domain and in the spatial domains. We'll see it, the laser structures, the laser characteristics to some extent. We'll discuss in details. And that times we'll see what is this DAB lasers. It is highly coherent lasers, and with this 1550 nanometer that is used in third generations. And you see still it is low loss. It is very low loss systems. It is 0.2 dB per kilometers. That's why repeater spacing is quite large. It is more than 100 kilometers, 100 to 200 kilometers are used in the third generations, right? And it is 1550 nanometers. In 1550 nanometers, interestingly, both attenuation and dispersion will be minimums. Here also photodiodes have been used like this 3-pipe compound semiconductors. And here also optical amplifiers started in these generations. This is a semiconductor optical amplifier. Next it is the 8-FA was used. The fourth generations, you can see almost same lasers are there, but WDM wavelength division multiplexing started. And another optical amplifier which is widely used at this moment also, 8-FA, erbium dot fiber amplifiers. This is used in fabric systems. A single mode fiber, it is around 0.2 dB or less, 0.1415 dB per kilometer. Also, it is being used in fourth generations. Repeater distance larger than the previous case. So mainly fourth generation based on WDM systems. Here, this figure you can see it here. Several components: input fibers, isolators, pump wavelengths. This is shown the how fiber amplifier is used. We'll see it. In fact, you need some pump lasers. Here you see pump laser. A portion of fiber is used for amplifier. It is shown here. So suppose signal is here. Say it is 1550 nanometer signal. It is used. You need to amplify these signals. Then how to amplify? There is no optical to electrical conversions, but you see using a portion of fiber which is EDFA, area bounded fiber amplifier. This can be amplified. Here you can see it here. Here is attenuated signals, and here it is amplified signals. Output, it is amplified. You can compare it, this with this. That is possible through this EDFA, which is maybe 10 meters to length, 10 to 30 meters, 30 meters in length. So in between this input fiber, output fiber, if you use this EDFA, then you can have amplified output, right? Amplified, same 1550 is used here, but with amplified output, you can have it, right? But for this, you need pump, lasers, other things are there that will see it. The different pumping mechanisms are there. It can be co-directional pumping, it can be contra-directional pumping, or can be dual pumping, etc. Different aspects are there. We'll discuss in details when we discuss the fiber amplifiers. So this is the fourth generations. Fifth generations, as I told you, this several generations have been also are being developed. Here, special type of lasers, vertical cavity surface emitting lasers are there at the same wavelength, 1550 nanometers. And here, DWDM system, most important is the DWDM systems. WDM systems, it is used in the 4 generations, different wavelengths. Here, optical interesting feature of optical fiber is for any other communication, you need only one carrier. But here, you see, you can multiple carriers can be used in optical fiber, since since it's based on light signals, so there'll be no interference here in this case, right? Because for interference, you need the coherent in natures, right? Should be coherent. Then only interference will be there. But if different lambdas are there, there'll be no such coherency. So there'll be no interference. So many wavelengths can be transmitted. So WDM generally it is 8 to 16 wavelengths. Beyond 16 wavelengths, it can be called dense wavelength division multiplexing. And you see, if you say instead of 1 lambda, if you say 10 lambdas, then you see 10 times your bit rate will be higher. Suppose for 1 wavelength you are getting say 4 Gbps, 4 Gbps if you're getting it. Then if you use 10 such wavelengths, then you see the 10 times will be bit rate will be increased, 40 Gbps. The same fiber can support all those things. So that is the WDM systems. And for dense wavelength system, it can be more than 100 such wavelengths can be transmitted. Right, yeah, you see it here. Dense wavelength multiplexings here, it is shown here. Right. So huge capacity you can have it in the of DWDM systems, right? And also here, apart from these EDFA semiconductor amplifiers, also Raman amplifiers are also there. In fact, there are different other amplifiers are there. Probably we'll not discuss, but to some extent I'll mention it. Raman amplifiers, Brillouin amplifiers. These are actually these nonlinear effects will be there. If you go for extremely high pitted systems, some nonlinearities will be there, and that times very difficult to amplify the lambdas. That times this type of amplifiers are called Raman amplifiers. For extremely high pitted systems, these are used. Right, 5th generation. Next generations, you see fiber system nowadays. Of course, it is implemented fiber to the home. Broadband tunable lasers are there. Bit rate is very high, and also people are trying with this. Already it is developed, but it's not in the market. It's based on Soliton systems, Soliton communication systems. There will be almost repeaterless systems. You can have it, Solitons. Soliton, it is just like particle, electron, proton, etc. Within a fiber, if you develop the solitons, then several thousand kilometers, you see maybe 4,000 to 6,000 kilometers, there will be no need of repeaters. Just imagine if it is the soliton based systems. Here actually in soliton systems, we'll discuss the certain systems. Solitary waves are there. Solitary wave can be converted to solitons, right? And a solitary wave, basically solitary wave, and it is called soliton. That is because it is just after collisions, the nature is same, just like electron proton. So that's why the name is called solitons. And in this, in case of fiber, dispersion is there, and dispersion we'll see it. Dispersion actually that actually if you launch some pulse, then this pulse shape will be broadened. That is because of dispersion, right? And there is another effect is here in optical fibers, which is the nonlinearity. That is because of nonlinearity, that that will increase the spectrum of the spectrum through the optical fibers, right? I mean, instead that times pulse shape will be narrow, right? Because of the generation of new frequencies. So if these two are compensated within the optical fiber, then this soliton can be developed. And if soliton is developed, that will be almost repeaterless transmission systems. Uh, it will be 100 times better than the present communication systems, right? So there the different generations are there. Optical fiber systems. These are the same things I mentioned. Different generation, different wavelengths, and different sources. We'll discuss in details. This gallium arsenide, aluminum arsenide is for low wavelength regions, shorter wavelength regions, and longer wavelength regions. It is actually indium gallium arsenide phosphide, right? And optical amplifiers are there. Optical amplifiers can be semiconductor based or can be fiber based. Fiber based means PDFA or erbium doped fiber amplifier. It is praseodymium doped fiber amplifiers. I mean, different rare earth elements are there. Praseodymiums, neodymiums. They are the different rare earth elements are there. For different wavelengths, different rare earth elements are there. Erbium are doped here in this case. Erbium, that is the rare earth elements. So based on these things, you can have a different fiber amplifiers. Photodetectors, generally for shorter wavelength regions, it is silicon photodetectors, and the longer wavelength side it is germanium photodetector. But nowadays it is indium gallium arsenide phosphide. It is indium gallium arsenide. This photodetector is widely used in 5G systems because you can change their the cutoff wavelengths by varying the composition mole fractions. Here germanium is say it is a responsibility is maximum at spectral sensitivity maximum at particular wavelengths. But here, in case of indium gallium arsenide, it can have wide spectral response regions. Similarly, silicon also its response is limited. It can be used up to 1.0 microns because of its band gap, right? You see. Band gap is cutoff wavelength is limited to 1.1 micron regions. Up to this, you can use it. So if you say 1550 nanometer, silicon cannot be used. So that time you can use either germanium or indium gallium arsenide. So different materials are there for different wavelength regions. This is the I think this is the last slide. Okay, the last slide you see it how 5G systems are being used in the SONET rings. You see these are SONET rings. I just mentioned OC levels, STM64, cross 64. They are the different bit rate hierarchies used. STM it is synchronous transfer model used in India countries. Here you see this is for this WAN, wide area network, and for local area network it is OC12 STMs, where through ATMs different servers, workstations, etc. they are connected to, etc. This is for less capacity regions, LANs, and this is LAN, WAN, and also in between there can be MAN also. Metropolitan area network. I mean, metro cities also can be connected. Several LANs can be connected through MAN, and several MANs can be connected through WAN. And that's what it is shown here. So you see that it means a local area network, metropolitan area network, and wide area networks. So LAN, MAN, LAN, MAN, and WAN. So all these are implemented. Can be implemented with the optical fiber. Nowadays, of course, it is present. All communication is based on these optical fibers in different regions, geographical. This actually considers the geographical. Within a building, it is generally land. Within a cities, it is generally man, metropolitan area network, and whole country, several cities are connected. That times it is WAN, wide area network. And that times you see different sonars are there. Anyway, today this much. If you have any questions, quickly, one or two questions are highly desirable. Any questions? If you have any questions, you can ask. I'm stopping these ones. Anybody, if you have any questions regarding these generations or any device, anything, if you ask. Any questions?
No, sir.
Okay. Okay then. Just wait and just taking your attendance, recording your attendance. Just a minute. Okay, it is 18th. 18th. Okay then. Next time we'll see it.
Thank you.